Let's explore the internal components of a capacitor. By delicately removing the outer plastic label and metal cover, we can reveal multiple layers of rolled paper inside. These layers can be carefully unrolled and separated. This rolled paper comprises two or more parallel conductive metal plates, each of which is connected to a terminal wire. These wires serve as the connection points to the rest of the circuit. Importantly, these parallel metal plates do not physically touch each other. Instead, they are electrically isolated by high-quality insulating material layers commonly referred to as the dielectric. The symbol representing a capacitor precisely illustrates this arrangement. Two parallel lines within the symbol represent the conductive plates, and the space between them signifies that the plates are separated by a dielectric layer. Using the water analogy, we can understand the behavior of capacitors more easily. Imagine two pistons, each containing water, connected by a pipe. When we apply a constant force to piston A, water starts flowing to piston B due to increased water pressure. This phenomenon is akin to the flow of electric current in a circuit. When a battery is connected to a circuit, electrons move from the negative terminal to the positive terminal. However, in the context of electricity, we consider current to move from the positive terminal, high potential, to the negative terminal, low potential. Here, we have an elastic chamber connected to a water pipe, acting as a barrier between two sides. Water from side A cannot flow to side B, and vice versa. We've dyed the water in side B with green color, but it can't mix with the water in side A due to the membrane's impermeability. This elastic membrane can stretch to a certain degree, allowing the piston to move based on the water pressure difference between the two sides. The membrane halts its expansion when the elastic force matches the applied force. Now that we've stored some energy in the membrane, if we disconnect the pistons and connect the two ends of the chamber, the membrane can move the water in the opposite direction and return to its initial state on its own. Initially, we store energy in the device, and then we can use the stored energy to do useful work. We can plot the membrane resistance force over time. Now let's examine the process in slow motion. Initially, the resistance force is 0. When we apply an external force, the resistance force doesn't increase instantly. It begins from 0 and then rises rapidly. However, as the membrane starts to expand, the rate of increase of the elastic force decreases over time until it matches the applied force. Now let's remove the pistons and connect the two ends. The force begins to decrease rapidly. However, as the membrane starts to contract, the rate of decrease of the elastic force slows down over time until it becomes 0. Can you predict what occurs with the water flow during this period? Initially, the membrane is in its resting state, almost as if there is no membrane present at all. Consequently, even a slight force can move a significant amount of water through the pipe. However, as the water begins to move, the membrane expands and starts to exhibit resistance to the water flow, causing it to gradually decelerate. This process continues until the water flow eventually comes to a halt. If we remove the pistons and connect the two ends of the chamber, the membrane can move the water in the opposite direction and return to its initial state. Initially, a significant amount of water flows in the opposite direction. However, as the membrane begins to contract, the force decreases, causing the water flow to gradually decelerate. Let's compare these two situations. Understanding this water analogy will help you better understand how capacitors work. The negative water flow indicates the water is flowing in the opposite direction. It's important to note that when we add water to one side, the same amount of water leaves from the other side. This is how a capacitor works. When we connect a capacitor to a battery, here's what happens. At first, the capacitor voltage is 0. Over time, the voltage gradually increases until it matches the supply voltage. If we disconnect the battery and connect the two ends of the capacitor through a resistor, the capacitor voltage starts to decrease quickly until it becomes 0. Now let's consider the current. In the beginning, the current is high. However, as time progresses, it diminishes and eventually reaches 0. If we disconnect the battery and connect the two ends of the capacitor through a resistor, a significant current starts flowing in the opposite direction. Over time, this current diminishes and becomes 0. Here, voltage behaves similarly to the membrane force, as seen in the earlier example. Similarly, current behaves like the water flow in the analogy. Now that we have a basic understanding of capacitors, we can explore their behavior further. When we store energy in a capacitor, it is known as capacitor charging. Conversely, when we use the stored energy, it is termed as capacitor discharging. Let's continue our exploration. We've modified our circuit to observe capacitor charging and discharging. Initially, both plates are charge neutral, resulting in zero capacitor voltage. If we turn on switch S1, current will flow, and the capacitor will start to charge. Let's consider what happens in detail. When one electron moves to plate A, its charge becomes -1, and another electron leaving plate B brings its total charge to +1. This slight difference in charge causes an increase in the capacitor's voltage. Continuing this process alters the total charge on both plates, consequently increasing the capacitor's voltage. The coulomb is the unit of electric charge in the International System of Units. 1 coulomb is equal to approximately 6 quintillion positive or negative charges. The capacitance of a capacitor is the amount of charge, measured in coulombs, needed to change the voltage across the capacitor by 1 volt. Capacitance is measured in units called farads. Let's assume this capacitor needs Q coulombs of charge for each plate to change its voltage by V volts. We can find the capacitance of this capacitor by dividing Q by V. The capacitance of a capacitor is typically labeled on the component, along with the voltage rating and other details. For instance, a capacitor might be marked as 100 volts and 470 microfarads. This means the capacitor has a capacitance of 470 microfarads. In simple terms, it requires 470 microcoulombs of charge to change its voltage by 1 volt. The voltage rating indicates the maximum voltage the capacitor can handle without getting damaged. In this case, the capacitor can withstand up to 100 volts. Let's revisit the construction of the capacitor. It consists of 2 metal plates, separated by an insulating material layer. The capacitor's capacitance, indicating the charge it needs to change its voltage by 1 volt, depends on 3 main factors: the surface area of the conductors, the distance between the conductors, and the unique permittivity of the insulating material, which depends on the material. We can calculate the capacitance using the equation. Capacitance increases with the surface area of the conductors and the permittivity of the insulating material, while it decreases with the distance between the conductors.